Thank you, Professor. Good morning, everyone. My name is Jarin Ritu, and I'm a PhD student here in the Department of Electrical and Computer Engineering. So I'm excited to present my work on efficient AI model deployment, especially using a technique called texture-informed knowledge distillation. To give you a bit more about myself, I am from Bangladesh, and I did my undergrad from Jahangirnagar University in Bangladesh. Yes, it's not working. Let me just pull up a bit higher. Can you guys hear me clearly now? Is it better? So yeah, I'm from Bangladesh. I did my undergrad from Jahangirnagar University in Bangladesh. And now I'm a PhD student. I'm a third year PhD student. And I work with Dr. People in our advanced vision and learning lab. And my research interest is like machine learning, computer vision, and image analysis. So to give you a bit more context about the research that I have been working on, so I've been involved in two research projects. In the left, we are in collaboration with MIT Lincoln Lab, where the goal is to develop deep learning models and algorithms for target classification. There we work with underwater acoustics, like ships, cargo, passenger ship, tanker, tug. Those are like different kind of ships. We have the sounds from the ships, and based on their sound signature, we try to classify the ships. And on the right, we worked with Baylor University. There we are looking at scanning microscopy images. So the goal is to like develop machine learning algorithms to measure the texture changes and morphological changes to the cell surfaces after we expose those cells into different toxic agents like nickel oxide, crystal cilia. So as you can see in both of my research work, the bottleneck is we need large foundation models to have like good performance. And what I mean by foundation models, so foundation models are large scale pre-trained models, which are like pre-trained on vast amount of data that can, so that the models can learn general purpose representation. And the model can be used in different downstream tasks. Like think of ChatGPT, we can input image or audio and ask our query so that ChatGPT can produce us like outputs. But this foundation model comes with a cost of lots of parameters, like billion, even trillion of parameters. So the models are very computationally expensive. It needs like high computational powers and large memory requirements. And that's been an issue when we try to deploy those large foundation model in real life scenarios or embedded systems. As example for underwater monitoring, people use like hydrophones where we have limited hardware requirement and like on limited GPU onboard access. Then in environmental sound monitoring, people uses IoT sensors or embedded edge devices where we need like a small and lightweight models, but we have to do a better job with that. And also in biomedical imaging, we often rely on portable devices that can give us like fast but efficient results. So in this space, knowledge distillation comes in. So knowledge distillation is a technique where we can use a large model's intelligence and pass those intelligence into a smaller network so that we can work with that small network and still can have like good performance as a bigger network. So knowledge distillation is a easy technique. The idea behind this, if you can see my pointer, so this is the small network that we have, and we will have a large network, which we will be calling the teacher model, and the smaller network, we're calling it the student model. So what happens in normal classification task? The student tries to learn from the ground truth. That's the hard targets. So in knowledge distillation, along with the hard truths, the student also try to learn from a large teacher model. So basically, large teacher model produce soft targets like feature representations or logics, and a student try to also mimic the behavior of the teacher, like how they are producing those. So there are different categories for knowledge distillation. So the first one is response-based distillation, where we only distill or transfer the knowledge from the last layer, the output layer of the teacher model. And then comes the feature-based knowledge distillation, where we distill the knowledge from the intermediate features of the teacher model. And the third one is relation-based knowledge distillation, where we just do not rely on the output level or the feature in the intermediate level, but also the student learns the relationship between samples and features in the teacher space. So if we look closely how these existing knowledge distillation methods are working, they're mainly focusing on high-level contextual information. Like they're either doing output layer distillation or doing feature distillation, but what they're lacking is like low-level structure and statistical textures. So we are proposing a method to incorporate those low-level textures in this knowledge distillation procedure. I will talk about more in details from the next slide. So when you think, when you hear the word texture, what comes into our mind, like how something feels like, right? So if you think of sandpaper, it's like a rough surface. The potato chips has a crispy surface, and silk fabric are like is smooth. So we can know by touching how the texture is for a certain object. But in the concept of image and audio data, we can also define texture, and model can also like distinguish between different data based on their texture. In the same way, like we differentiate with different objects. So if you see, in broadly, we can divide the texture into two parts, a structural texture and a statistical texture. So for the structural texture, if you think of an image space, so it's a bit easier to know about the structure of an image. If you see this image, we can see by it a spatial arrangement of the pixel intensity values. That's the structure. So these things can be replicated to audio domain too. In audio, we can think of periodicity of a certain audio signal as its a structure, like how the periodicity repeats over some time and space. That's the structural texture that I'm mentioning. And for the statistical texture, for the image space, we can like count the gray level co-occurrence values and plot a statistical histogram out of the co-occurrence intensity values. That's the statistics from the image. And also in audio data, we can calculate the amplitude value as the same as the pixels in the image. That will be the statistical texture for audio space. So my research objective of this work is, the first one is developing a texture-informed knowledge distillation framework, which will include a structure and a statistical knowledge into the distillation process. The second objective is evaluation. So I will evaluate my knowledge distillation framework with the state-of-art existing KD methods that we already have. And the third one is like quantifying. As we incorporate those structures, so we want to know how much contribution it has, like each knowledge component, a structure, statistic, distillation, and classification, always be there. And the last objective here is assess, which is like we want to see how generalized this framework is into different domain for different tasks, like audio classification to vision segmentation. So we are calling this framework is SSATKD, which is for statistical and structural our texture knowledge distillation. So when I will be using this framework in audio space, we are calling it SSATKD-A. And when I will be using this framework for vision task, we are calling it SSATKD-V. So for the first objective, which is the development phase, I will be talking about how this overall SSATKD framework works, and what is inside the statistical and structural texture module. And then I will be talking about the experimental design of the experiments. So here's the overview of the whole SSATKD framework. So we have a student model up in here, and we have a large teacher model. It can be any large CNN models or any foundation models like Hubert, Whisper, and Wave2Vec2, the foundation model that we have. So the process is, in normal distillation, what happens after the last output layer, we distill the knowledge from the last output layer from the student and teacher. That's the distillation loss. It's the regular distillation loss. But along with this distillation loss, I will have like two more losses for each of the texture. One is for statistical texture and one is for structural texture. So given an input, the input will be passed through teacher model and both the student model. And after the second convolution layer of the student network and also the teacher network, I will be extracting those feature maps, because like texture are more prominent in the earlier stage of the network. That's why we're extracting from those earlier layers. So after extract those features from the second layer of student and teacher, we will distill the knowledge. We will extract some structure and statistics from the feature maps and distill those knowledge in between teacher and student. And finally, as I have like 4 loss components in my framework, so I will have like 4 losses. I will talk about the loss in details going forward. So let's first see what is happening inside the statistical texture module. So after we have the feature maps from the second layer for student or the teacher model, first I will calculate the global average pooled feature for the entire feature map. So global average pool feature will act as a statistical summary for the whole feature map. So, and then after we have the global average pool feature, we will calculate the cosine similarity. So cosine similarity will like measure how each local region of the feature map is aligning with the global structure of the feature. So after we have that cosine similarity, I will reshape the cosine similarity into a 1D vector so that it will be easier to process and analysis. And after we have the 1D vector of cosine similarity, we will quantize the cosine similarity into different bins. You can think of it like grouping same feature activations together. So after I quantize those feature maps into different quantization bins, then I will calculate the co-occurrence between different bins. So the co-occurrence will give us like how like one feature map is occurring with another one in a same neighborhood, how often. So it will give us the joint probability of feature activation occurring. So at the end, we will have a 3D feature map output from this statistical texture module. So in this 3D feature map output, you can see n by n by 3. So n by n means like co-occurrence in one direction and co-occurrence in another direction, and the third direction will be like the counting number of the co-occurrence. So here is the visual representation of the co-occurrence map. So here the like light color are showing we have like more co-occurrence in those areas, and the darker colors are showing we have like less co-occurrence of feature activation in those areas. Moving forward to the structural texture module. So what is happening inside structural texture module is, given those input feature map from the second layer, first we are applying Gaussian decomposition. So it's a multi-scale decomposition. It's a very well-known image processing technique where we decompose the image into its smoother versions. So after we got the Gaussian decomposed feature maps, then we will be calculating the Laplacian feature maps. So Laplacian feature maps will highlight the edges of the feature maps. And after we have like this Laplacian feature map in each stages, we will apply edge detection module, which is consisted with Sobel kernels. So Sobel kernels helps with detecting edge in 8 direction. We can detect edge in 8 direction. So we will have like for each of these Laplacian feature map we will have 8 directional edges. So at the end, we will combine those 8 directional edges into one, and that will be the final output of this structural module that will preserve the fine details and also the edges. So as I already mentioned earlier, so I have multiple components in my total SSATKD framework. So the first one is classification, as I will be doing a classification task. It's a supervised classification loss. So for the classification laws, I am using the regular cross entropy loss. So cross entropy loss, through the cross entropy loss, the student tries to learn from the ground truth level. And the next one is the statistical loss. So for the statistical loss, I am here using its earth mover distance loss. It's called EMD. So it's quantify the changes from the student and the teacher distribution. So EMD measure how much effort will be needed to shift like one distribution to another, to align with another. But it can be computationally expensive because we do it by calculating the cumulative distribution functions. So the traditional EMD, in the traditional EMD is 1D. That means like we can have the measure of like how much mass we need to move from one direction to another direction, but it only can work in one direction, like in one line. We can go to left or right to match the distribution, but it doesn't count about the up and down direction. So as if you remember the statistical map from our statistical texture module, it was a 3D map. So we have like both co-occurrence in both direction. So we need to account for like both directions. So we extended the idea of 1D EMD to 2D EMD. And this is like the one direction for one co-occurrence, and Y is like another direction for other co-occurrence. So our teacher and students feature maps are presented in like 2D histograms here, and the points you're seeing, it's like it's the co-occurrence counts. So we need to shift this whole distribution to this space throughout this EMD. And this concept is presented in this mathematical formulation, where we have to like calculate CMD of teacher and student and take the difference, and that will give us the measure of how much mass we need to move. And then we need to multiply it by the ground distance. So ground distance will tell us like in which direction we need to move. Is it up or down? Is it left or right? So in total, that's how we will calculate the EMD loss. The goal is to like align the student's distribution with the teacher's distribution. Yes, Professor.
So how common is these compare distributions with like the tail or like
Yes.
what
Yes, so like the most popular choice is scale divergence. People use it for distillation, but the thing is scale divergence works point to point wise. So here, if our student and teacher have like different bins, so in this case, EMD will work better because it will shift the whole distribution. It will not calculate like point to point, bin to bin analysis. That's why we chose EMD, and we also have some ablation studies to later on show if EMD is working better or KL divergence. Thank you for the question. Moving forward, the third loss is the structural loss. And for the structural loss, I'm using cosine similarity loss. So cosine similarity measure the angular alignment between two vectors. So if you remember from the structural module, we have those teacher and students output. So we will calculate the alignment between teacher and students. So the benefit with cosine similarity is it's only only about the direction, not the magnitude itself. So if the student has like weaker feature activation, but it's in the same direction as the teacher, so we will have like high cosine similarity. As a result, our loss will be low. But if we have like different direction, the student's alignment is in different direction, then we will get like low cosine similarity with teacher, and we will have high losses. And the last one is distillation loss, which is, and again, I'm using here the EMD loss, art mover distance loss that I talked about, but here it's 1D, the regular EMD, because we are computing the output probability distribution of teacher and student. So we have like 4 losses, and for each of the loss term, we have a weight. So what we do is we can assign like weights manually here, or we can train the weights during the optimization process. So here we are training the weights based on an uncertainty based weighting. So what is happening here is for each of the loss term, we are calculating the variance of the losses. So if a certain loss term has like high variance, that means it's a bit unstable. So it will be assigned to a lower weight. And if a certain loss has like low variance, that means the model is stable. So it will be assigned to a higher rate. And the weights will be jointly optimized throughout the training process. So that was the framework development part. Let's move into the experimental design. So first, like for the data set, I am using 4 sound data set. The first one is sheep data set, deep sheep and BTUAD. It contains the sound from different sheeps. And the last one is environmental sound classification, ESC50, and urban sound 8K. Those are environmental sound data set. So data pre-processing technique is similar for all those data sets. So given an input signal, we are resampling the signal first to a fixed sampling rate, and then we are dividing the signal into smaller chunks. Could be 3 seconds, could be 5 seconds, could be longer or shorter. And then from the audio segments, we are extracting this log-mail spectrogram. So log-mail spectrogram, it's a 2D representation of a 1D signal. It's like an image representation for the audio. And this is the audio feature. It's called log-mail spectrogram. And this will be the input to our model, to our SSATKD model. And then we will do the classification. For the models choice, for the student model, I am using this HLTDNN model, and for the teacher model, I am using two sets of teachers. The first one is pre-trained audio neural networks. So these networks has CNN backbone. The first one is CNN 14, ResNet 38, and MobileNet V1. And the other set of models are foundation models, which is Wave2Vec2, Hubert, and Whisper. So as you can see, the student model is very small. I will show the parameters, how many parameters those models has, and these are like an example image of CNN 14, and this is an example image of Whisper.
What are they? What are?
Yes. So yeah. So for the student network, I'm using this HLTDNN. It's called histogram layer time delay neural network. So time delay neural network is like a 1D network to process audio signals. So if you see the upper network, this is regular TDNN network. So we added a histogram layer in parallel to the TDNN after the fifth convolution layer to extract the statistical information in it, and we called it HLTDNN model. That's our student, yes.
How do you take two models with two different architectures and pull their feature maps and collapse them down into a space that's terrible?
Yes. So that's what I am trying to say. Like texture could be a universal lens. So texture is same. It doesn't matter on the architecture, but underlying texture should be the same for a particular data. That's what we are focusing on. Mm-hmm.
You have a larger model, you're gonna have, say, like more feature maps.
Okay.
Like how do you, I think that's your
That's
question. How do you-
okay. Yeah. So we are like matching those spatial dimension of the feature maps before processing the texture by a one-by-one convolution. And for the spatial dimension, we are padding or interpolating the feature map to match the spatial dimension. So the sizes are same before we pass those second layer feature map into different texture modules.
And was n by three.
Yes.
Is that correct, the final space that you're documenting?
So we are seeing which one is smaller, student or teacher, which one is smaller. We're matching the other one to that size so that the computation will be easier.
Yeah, go back to. Go back.
Yeah.
Yes, here, this is more of a question.
Yes, this one, right?
Yes, the question was asking is that n by 3, are you using that within the wall?
Yes, I am using that n by 3, but that n by 3 could be different numbers for student and teacher model because they has different architecture. So for the layer, for output from this layer could be different because there could be different number of channels there, different spatial dimension. So after I extract those feature, I am comparing like which one is smaller and matching the other one into that size. So both size are same before like passing into these texture modules. Is that what is the question? Uh, yes, so the student model here is a histogram layer HLTDNN. And for the teacher models, I mean by pre-trained audio neural network, these are called PANs. These are trained on audio set data set, which is a large audio data. ImageNet. Mm-hmm. It's kind of, yeah, it's kind of ImageNet for audio, general purpose images from internet. So moving into the second objective, which is like evaluate how my framework is working against of different state of art KD methods that are already existing. So for that, first I will show the baseline performance without doing any knowledge distillation. How does the model works for classification? And then I will show the results after doing the distillation. And then I will compare my SSATKD framework with other state-of-art knowledge distillation methods. First, let's see the baseline performance. So this is direct doing classification without any distillation. So for the student model, you can see the parameters are very less. It's 11.3K. And the teacher models, the parameters like starts from 4 million and goes up to like 96 million parameters. And as I mentioned, I have like 4 data sets. So I presented results for all the 4 data sets. So you see the student model for in DeepShift data set, it was like 59.62%, whereas with the teacher, we got the highest 71.33%. And for VTUAD, student had like 80%, and ResNet 38 was 97%. And it's true for all these 2 data sets. So the goal here is, after applying distillation, we need to achieve like similar kind of performance like the teacher model with only the student model. So let's see how it goes after distillation. So this is the result after doing distillation. These all are student model results. So for when we had like no distillation, the accuracy was 59.62 for DeepShift dataset with 11.3K parameters. But when we do distillation, we get the highest accuracy 66.22 with mobile VNet 1 teacher. And the parameter increased very little, 1K. And the parameter increased because of that 1-by-1 convolution we had before passing those feature maps into the texture modules, because we need to fix the sizes in between teacher and student. That's where the parameter increased. And as I mentioned, the goal was with the student, we need to achieve like similar performance like a teacher model, but with less number of parameter. So we achieved 66.22. If we go back and see, the mobile VNet was 66.64% accuracy. And now with the student with only 12.3K, we are achieving 66.22% testing accuracy. And if you see for the VTUAD data set, before with the student, we had 80% accuracy. Now it increased to 86%. And for ESC50 from 72 to 80%, urban sound 88 to 91%. These are like the average gain that we have for all of the data set. So as you can see, all the average gains are very statistically significant. So we had like a very boost in performance after doing the knowledge distillation. Now moving to comparison with like already existing KD methods. So the first one is vanilla KD. So vanilla KD is the first KD method where they like distill only the output layer logics in between teacher and student. So vanilla KD got 61.23% in DeepShift dataset. So for this study, we chose DeepShift dataset and did some further ablation studies. And the next one is SRD, which is semantic representation learning, which was again 61.99%. TFKD is teacher-free knowledge distillation, which was 60.33%. CRD and CCKD is like constructive and correlation based distillation. Both were 61 and 60%. PAD is like attention based distillation, which stands for prime hour adaptive distillation, which was 52.25%. And if you see like SSATKD, it outperformed all the other 6 methods that I compared with at 65.92%. That verifies like our incorporating texture is helping. So going to the third objective, which one was like quantifying, like how these different knowledge components are affecting the performance. To measure this, I did an ablation study into 3 loss function that we have. So we are doing classification. So classification will always be there. The first row is classification. And then I did like all the possible combination for the 3 loss term. The first one is like distillation. It's doing only distillation, not any texture in it. It has 65.99, which proves like knowledge distillation itself boosts performance from the baseline models. And then when I add like a structure, so we are just distillating the structural texture. And the performance is 65.92. But when I incorporate the structural texture with distillation, we got the highest performance, which is 67.46%. And then when I only distill the statistical texture, we got 65, and when we incorporated statistical texture with distillation loss, and it goes a bit down to 61.85%. And then when we incorporate only like texture distillation, not like output distillation, it's 64.84. It's still pretty similar to like only distillation. But when we incorporate all the things together, then it gives us a nice balance of 66.22% testing accuracy. So the last objective of my work was like of assess its generability in different domain. So till now I worked with audio data and did classification tasks. Then I will use the same framework to do vision task, which is segmentation. And for the segmentation, I chose this microNet dataset. It's a scanning electron microscopy dataset. It has like two subset of images. The one for nickel-based superlay images, and one set is for environmental barrier coating dataset. So I am using only one subset for this purpose, because this is still in a like initial phase of development. So I will be showing some preliminary results showing how this SSATKD work can be used for vision task. So for this purpose, I am using a tiny version of the UNet model. So as you can know, UNet is the most popular segmentation model. So I'm using a tiny version of it with less parameter. I will show it. And for the teacher model, I'm using the micro segment anything model. So segment anything model is a foundation model for doing segmentation, and micro segment anything model is especially for microscopy images. So the process will be similar. I will now have the image and the annotation. So in the audio space, we had the audio and the ground truth. So here for segmentation task, our mask or annotations are the ground truth and the image. I will pass those image and annotation throughout the SSATKD framework, and I will do the segmentation. So if you see the image, so we have like two classes to segment it out. One is like the blue class, it's the large class, and one is the red class, which are the like smaller classes. So these are the segmentation performance with SSTKD P. So when I did like only student, only tiny unit architecture, which has like 29.8K parameters. So I put it the IOU and DICE score. So it measures like the overlap between the output and the ground truth. So we need to both of the values to be higher to see the segmentation quality is good or not. So if you see the student model for the large classes, which are like the blue ones, it did 68.75 and 81.45, but in the smaller classes, which are like these small red things, it did pretty bad. It's like 0.18 or 28. It couldn't like segment it out kind of anything. But for the teacher model, which has 93 millions of parameters, it did a pretty good job in like the bigger class, the blue classes. It's like 93 and 96%. And for the smaller class, it also did better. It 68 and 81%. But after I do the distillation, this is the results for the student model. So the parameter again increased from 29.8 to 30.3K. And if you see the performance for class 1, it like increase it almost like more than the teacher model itself. Teacher model was 0.93, and now with the student model with this less number of parameter, we are getting 0.994% accuracy. And this is very noticeable in the smaller class, where the smaller class student perform very poor, but after distillation it has a very big boost from 0.18 to 0.75 and 0.28 to 86. So I also have a visual representation of the segmentation so that we can see it qualitatively. So first column is like the original image, second one is the ground truth, and this one is like after doing distillation, tiny unit how it performed, and this is like after doing distillation how did the performance increased. So if you see the black boxes here, the student over segmented some regions, but after doing the distillation, it did the segmentation perfectly. for this a small object, if you can see it, for this blue object. And also for these purple boxes I'm showing, where there was a very little object to be segmented out, which the tiny unit model couldn't do before distillation, but after doing the distillation, it could segment it out those little tiny regions. And it's true for like all the image. In this subset of data set, I had like these 4 test images, so I put the results for all of the 4 here. So that was all from my work. So we see how knowledge distillation helps like transfer knowledge, and also how incorporating texture in it can boost the knowledge distillation performance itself. So my future work is like extend this framework for self-supervised distillation, and also adapt this framework for doing different downstream tasks like object detection. And we already have a paper that the results I showed to you, and our paper and code is available in the GitHub repository. You can scan the QR code and it will direct you to the paper that we have. So I would like to talk about the collaborators. So here in Texas A&M, I work with Dr. People, as I mentioned earlier, and my other lab mates are Amir, Atharva, Bomi, Jack, and Aditya. And also I worked with the Baylor team, where I work with Dr. Says, and she has also some PhD students and undergrad and master's student, Taylor, Dominic, and Kiara. And these two are like our funding sources is MIT Lincoln Lab and Texas A&M University. And I also used TAMU HPRC high performance computing for my experiments. Thank you all for listening to me. If you have any questions.